Wanted to just take a second of review, okay? And so, in the development of what the atom looked like, okay? An atom is the smallest element, or the smallest piece that actually has chemical properties, okay? And so, the idea developed well before modern scientific processes, but was just a thought experiment that was validated by experimental evidence. And so, if we talk about the first person, that really is part of this process that we talk about in modern terms, we talk about Dalton. Okay, Dalton came up with a whole set of things. And so if I talk about Dalton, what did his atom look like? Do you know its shape and what he thought it looked like? Yeah. Yeah, it was basically a circle, well, three-dimensional circle, a sphere. Okay, it was a little ball bearing, completely full and uniform throughout. So it was a solid piece that was a sphere. Okay, and it was neutral. Okay, so no charge. All right. The next idea came after the idea of radioactivity. Okay, radioactivity, by the simplest definition, is that the atom, okay, and in particular we found out later the nucleus is unstable and throws away things. Okay, in essence it either falls apart or throws away energy. Okay, and so what we found were elements that were radioactive, or materials that were radioactive, and they were throwing out little tiny particles and energy that were smaller than the atom. And we found that there were some particles that were negative, some particles that were positive, and some particles or things that actually had no charge. And so the idea was that the atom must not be the smallest thing. Something must make up the atom, but those things don't have chemical properties. And so the idea was Thomson came up with, okay, spelled weird, and he came up with something that was an idea based upon a dessert. What theory was his? Plum pudding, okay? He thought it was a sphere also, okay? He thought it was solid, sphere, but what he had in it was the largest part was positive, because the particles that were positive were huge, and then it was dotted with little tiny things that were negative. But we still had a solid material, okay? And then someone went and did an experiment with some gold foil, kind of like aluminum foil, but a little bit more expensive, okay? And so the reason why they used gold was because gold can be beaten in a very, very thin sheet. Aluminum would be too thick. We can't make aluminum that thin. And so Rutherford, okay, he came up with a whole different idea, okay? It was still a sphere, but what in the world did Rutherford have as his model? It was a sphere. What did he find? What was in the center? He called it something. A what? A nucleus. So in the center of his idea was a nucleus. And how big was the nucleus? Yeah, really tiny. Now, what is the size of really tiny mean? All right, if you think about the football stadium, Neyland Stadium in Knoxville, where the Vols play, okay? The outside nosebleed edge row of seats, okay? That's the size of an atom. The nucleus would be the size similar to somewhere between a marble and a baseball, okay? He said all of the mass is in that nucleus. Okay? Right there, the nucleus has all the mass. Come on. You can work. Okay? It also has all of the positive charge. On the outside, in the sphere, all right, has the little negative charges, and he called them electrons. And so, essentially, it was a sphere, but it was totally empty space for the most part. These little negative particles called electrons fill those tiny spaces. They buzz around kind of like bees around a hive. They're buzzing around. Now, Rutherford's idea about the atom essentially is our idea about the atom, except for he thought the electrons were everywhere, taking up all of that space. We're going to find it's a lot more organized, but essentially the nucleus with all the mass in the center and the electrons on the outside so small that they really weigh nothing in our calculations in CHEM. Physics, we have to account for its mass. Some of the physical chemistry, we might account for its mass, but for our purposes, it's so small it doesn't matter. Okay? The nucleus had all the mass, had all the positive charge, but what else did we find in there? Electrons in the big volume. What's in the nucleus? The two things. Protons. Okay. Protons that had a positive charge. And what? Neutrons that were neutral. And they were particles that weighed about the same mass. So they both weighed about the same. All right. And that's our idea of the modern atom at this point in time. And when we look at it, we know we have three things inside the atoms. The different combinations of them create different items or chemical elements that behave differently. We have protons and neutrons in the nucleus. We have electrons that are around the nucleus. We know that they actually have an amount of charge, okay? But we kind of rounded to this, either positive 1 and negative 1. Okay, neutrons was 0. We know that they actually have a true mass, but we can relatively give them a mass. And so the proton is 1.0073, the neutron is 1.0078, and so we just round that to 1. And look at the mass of the electron. It would take about 1,800 plus electrons to even equal 1 proton. And so we calculate that, we round it out to be 0 because we have nothing that has that many electrons. And so we know that inside every element on that periodic table that we could determine electrons, protons, and neutrons based upon just looking at the periodic table. Okay. And then there are some symbols about what we designate them. Okay. A proton has in it, okay, a number that down here is a number of protons. That actually identifies what the element is, fundamentally. This up here is the mass. Okay. This one's called the atomic number. This one is the mass. And the mass is protons plus neutrons. Okay. This number up here is the charge. And in this case, if I just talk about a proton, it has one proton. It has no electrons. When I add up the number of positives and the number of negatives, a 1 plus 0 is a plus 1. That's why it has a charge. The electron, designated by a small e, all right, its mass, 0. And what we're going to see is that it doesn't have an atomic number, and this is an oddball case, okay? It doesn't have a proton, but in the case of what happens when an electron comes from the nucleus, I'm going to lose a proton. That's why it's a -1, okay? And in terms of a neutron, it has no protons, but it does have one mass. It is also 0 charge. And so we're going to use these to designate what happens. Now, where in the world does the radioactivity come from? There are 3 types of radioactive material. Okay, there's going to be alpha, beta, and gamma. We'll come back to that in a moment. Now, if we are looking for the protons, neutrons, and electrons, okay, then depending upon what we look at, okay, in terms of an elemental form, I'm going to be able to solve how many protons, neutrons, and electrons there are. Now, does anybody know what the element CO is? Cobalt. That's good. All right. Now, cobalt, of the numbers that I give, this is kind of oddball. Okay. I wrote cobalt, and I did this because it's what CHEM-111 told me. Normally, if you do not have a charge, you don't put a 0, because chemists are lazy, we just leave it off. But I did that to really point out this has no charge. Okay? I gave you which of the 2 other pieces of information. Is this the mass or is this the atomic number? The mass. Okay? Why in the world did I not give you the atomic number, and why do we not usually write the atomic number?
The atomic number for any element stays the same to their isotopes, which change the number of neutrons.
Right. For every element, the number of protons never changes. So if you have the element itself on the periodic table, okay, I can't change that. So the number that for cobalt is its atomic number is what number on that periodic table over on that wall? 27. Okay. So I'm going to go ahead and just, for clarity, put it there. But if you write the symbol, you don't have to write that atomic number, because if you ever change the symbol, you change the atomic number. Okay, so it's a given. We write mass because mass can change. Now, on the periodic table, you have 2 numbers written on there. All right. For cobalt, it says 27. And what does it say below it? You've got really, really good eyes. For real. 58.9 and something or other, right? All right, so 58.9. In the case that I gave you on this problem, did I put 58.9? No, I actually gave you a whole number, because elements have to have a whole number. Well, why in the world is it a decimal over there? Okay, cobalt exists as 59 most of the time. But there are some that were on a diet and weigh 58. And so what I do is I represent in nature, if I took a handful of cobalts, what would the average weight be? And that's why we get 58.9. You know, on a periodic table, the mass number is always the decimal. The whole number is always the atomic number. Okay, so that's a given for you. And if you are asked to do protons, neutrons, and electrons, what you're going to do is you're going to round it to the closest whole number, okay, to do the problem, or I will define exactly what mass you're going to use. So if I ask you just to pick it off the periodic table, I want the most representative one. And then cobalt's case would have been 59, because I would have rounded. That was the closest whole number to round to, okay? And so I'm going to find out a whole bunch of things about this. You're going to find the pin for this, P-E-N-N. How many protons are in cobalt here? 27. I have 27 positive things inside this atom. How many negative things, electrons, do I have to have? I have to have 27. The reason being, it's neutral. I have to have enough positive and enough negatives to neutralize each other out. How in the world do I find the number of neutrons? Well, the mass is equal to the number of neutrons plus the number of protons. I know one of those on this side, 27. I know on this side, 59. And I solve for n. Mathematically, what do I do to solve this equation? Oh, this is why we have to have you know algebra before you come to this class. Okay? And so, if you pull out your calculators, what would you come up with? 32. And those would be neutral. Okay? Its charge is 0 overall. Okay? Beautiful. So, let's see, what does that mean in real life? Okay? Oh. That wasn't exactly what I wanted to do, but I did it anyway. Okay. Let's go here. Let's work my homework periodic table. I'll work on this. And cobalt is right here, work problem. And it asked me, number of protons. You told me it was 27. Number of neutrons. You told me it was what? 32. Atomic number was 27. Number of electrons in this one, you told me it was 27. The mass number for this one is 59. And, okay, charge. You have to put it in terms of 0, a negative for a -1, and then number and the charge. And we said this was 0. If you put O, it's going to be wrong. Okay, so let's see how well you did for me. And I get a little angst every time, you know, for reals. And good, you have helped me. I feel so much better about myself now. All right. Let's do this next one, carbon, P, E, and N. Now this carbon, if you went to the periodic table, what would be the mass of carbon just normally? 12. Okay. Is this the normal version, the one that you find most often? No, but I defined it for you, right? So, how many protons are in carbon? 6. How many electrons are in this carbon? It has to have 6 negatives because it's neutral, right? How many neutrons in this one?
7.
Would be 7. Because protons, 6 plus 7, neutrons equals 13, and its charge is 0. All right, what about this one? P, E, and N. How many protons for hydrogen? 1. How many electrons for hydrogen? Okay, in this case, I have 1 positive, and I'm going to say 0 negatives. The reason being, the charge is positive. Okay. How many neutrons would I have for this one? 0. The mass is made up of only the proton. There's no neutrons in this version. Okay. And I have a charge of a positive 1. P, E, and N. This element is oxygen. How many protons? 8. Good. 8 positives. How many electrons for this one? You have to have 10 negatives. Because if you add 8 positives and 10 negatives, you end up with a -2. Okay. How many neutrons? 8. Is oxygen 16 the one that you would have used if you just had the periodic table? Yes or no? Yes. Okay. Are these problems hard? How many of these problems do you want on the test?
All of them.
All of them, right? We won't do that, but we'll give you a few, okay? And it will be just as simple as that, okay? Once you figure out the strategy for every problem, it will be simple, yes?
Are we giving a periodic table?
You are going to have a periodic table, yes. You'll have a periodic table for every exam, and what we really want you to do is be able to read that periodic table, okay? It will be a nice clean sheet, nice clean periodic table every time. All right, now let's move on to the next idea. All right, of the different 3 types of radiation, alpha particles, a beta particle, and a gamma energy. An alpha particle was positive, it had mass, and it was a piece of something that was falling out of the nucleus. That piece of something was a helium nucleus. Okay? A helium nucleus has 2 protons and a mass of 4. So that means it had to have 2 protons and 0 electrons. And that piece broke out of the radioactive material and flies off. When that happens, the nucleus that is left changes what element it is and becomes a little bit more stable. Sometimes one radioactive and what's called decay, because the nucleus is falling apart, it's decaying, makes it stable. But most of the time it takes multiple things to make it stable. Okay? And so that is one of the ways that can actually have radioactivity. The second is a beta particle, which is essentially an electron that flies out of the nucleus. Okay? Well, is there an electron in the nucleus? No, there isn't. And so what happens is, where does the negative come from? It actually comes from a neutron that is neutral. And what the neutron does is it throws away a little particle that is negatively charged. If it is neutral and throws away its negative, what is it left being? It was neutral, threw away the negative, it's left as being a positive. One of the neutrons actually gets converted into a proton by throwing away the negative charge. Okay? And that's beta decay. Gamma decay, we found, had no charge. It is just energy. Sometimes the nucleus is unstable because it has too much energy. It throws out an X-ray. Well, sorry, it's called a gamma ray, not an X-ray. It is similar to an X-ray, but it's more powerful and more dangerous than an X-ray. But it's just energy. And so we can show what happens in a decay, a nuclear decay, by showing you exactly what we started off with. What is this element? Uranium. Uranium that weighs 238. So we usually call it 238 uranium. It undergoes a beta decay. So it throws away this. When it throws it away, that means the nucleus gets smaller of the atom. And so what you do is, this can be just like a mathematical equation, and you can put an equal sign here. And so if I take 2 away from 92, I end up with 90, mathematically. And remember, whatever the number of protons defines what the element is. That's where I can change the elemental symbol. Okay? And then the weight, I lose 4 of them, and so the weight becomes 234. And so when you add up whatever fell off plus whatever is left over, it should equal the beginning. Okay? And what you need to know is that is an alpha decay. Okay? The alpha particle, 4-2 helium. Okay? 2 protons, 2 neutrons actually fall out. The atom gets smaller in its nucleus. The radioactive decay, radioactivity, good or bad?
Pretty bad.
Pretty bad?
Depends on the circumstance.
Depends on the circumstance. Radioactivity is natural. Okay? There are lots of radioactive material in the ground all the time, decaying. Something that we can't control. Okay? The instability of the element. It was there when it was created, that instability. Okay? It can be bad because the things that fall off have high energy. And that have high energy can hit us, and if it hits us, it could cause damage and cause a disease, like a cancer. Now, it's normally okay if it's in nature, but if we concentrate radioactivity into a small little space, it becomes very radioactive, and that's dangerous. Don't want to be around something that's highly concentrated. Well, why would we highly concentrate something? To make a power plant or to make a bomb. And that has a whole other issue about it not being so great for us. Okay? But radioactivity is everywhere. Now, there are different levels of issues. Okay? For alpha particles, they're so large and come up with not as much energy that layers of skin or clothing can actually protect you from that. Okay? Don't eat it, because then you have no protection and it's inside of you and it can hurt you from the inside. But then again, don't eat any chemical in the lab, or don't go to the ground and just grab rocks and eat them. Okay? So you protect yourself by just not eating stuff. All right? And so, alpha particles can be stopped fairly readily. Beta decay. Carbon-14. Have you ever heard of C14? What is C14? What can we use C14 to do? Radiocarbon dating. We can actually date how long something has died in the past. Okay? Ish. Okay? There's some issues with it. There is a fundamental scientific principle that can be used, but there's a whole lot of assumptions when this particular one is used. The beta particle comes out with a little bit more energy. It's smaller. That means with more energy comes more damage, and it actually can be stopped by a thin sheet of aluminum or even some layers of clothing. A lot of times we use plastic to protect ourselves, but it's a little bit more dangerous. If it hits your skin, it can penetrate a little bit inside of you, and so they can cause damage. In this case, a beta decay is a little negative charge. Okay, here's where it stops. Okay, and when you do the mathematics, if you make an equal sign, is that -1, then this must become 7, because 7 minus 1 is 6. Changes the element to nitrogen, but it has no effect on the mass. The reason is, I do have more protons, but I have one less neutron. So it just swaps out 1 for 1. Okay? So, beta decay, we use this quite often. Most of the materials beta decay very quickly away, and you just need to be a little bit cautious. The last is gamma radiation. Oh, this is appropriate. I use green. All right. Why do I say green and gamma are appropriate? The Hulk. He was exposed to gamma radiation. Has nothing to do with real science. But it is a very dangerous energy. All right. You can stand behind a lead block. It'll go through the lead block and come hit you. Okay. And it comes with enough energy to strike your DNA and rearrange it. Not a good thing. We do not want to be around gamma radiation. Now look at the element. The element that before the radiation decay and after doesn't change, because there is no mass, there is no particle, it is all energy. This version is a little bit more stable than this version. Okay? You can't tell it by what I write, but in reality, it's just a little bit more stable because it's given up its energy. All right? If you take a look at these particles, okay, the sizes of them, the alpha particle is rather large, the beta particle is smaller, and there's no size for the gamma, and it can go through multiple things. But they are influenced, and you saw a video about this, by electrical fields or magnetic. You can use a magnet or electrical fields. Some are attracted towards the negative and away from the positive. Some are attracted towards the positive and away from the negative. The principle is this. Opposites attract. A positive and negative try to attract. And a negative and positive try to attract. but the similar try to repel. So two positives repel each other, and two negatives repel each other. And so they can be isolated and characterized differently by looking at material that threw out radioactivity and can be separated by charge. So, what would be the product up here? What would I write as the particle that fell off in the first one? Helium. That has a mass of what? 4 and number of protons of 2. Is that a beta or alpha decay?
Alpha.
Great. Next one. It would be an electron. How much would it weigh? 0. And what would its atomic number be? -1. And that is a beta particle, right? Do you want some of these on the exam? Yeah, this one's easy. Okay, next one. Beta or alpha? Beta. An electron, 0, -1, beta. The last one. Alpha. A helium nucleus that has 2 protons and weighs 4. Okay. These shouldn't be ones that stump you. Okay. This should be a real quick, I'm going to get my points and move on to the next question. Uh-oh, let's write out this one fully. All right. Uranium. Right. Uranium. Right. 235. Right. 92. Yields. All right. What in the world do I do here besides panic? Okay. Well, it's an alpha decay, right? So I know the second thing that comes off. I know that 4 and 2 helium come off by definition. Got that? So what is the first number that I really need to determine? The number of what? Protons? And then, so we can know the element. So how many protons are on this product? 90. What is the element that represents 90? Would be thorium, the thunder god element. And how much would it weigh? 231. Now, look at the periodic table. Is 231 the normal thorium? No. What is, if I actually made you go to the periodic table, what would you say the weight would be? 232. So it's not a normal version. It does exist, but it's not a normal version. Most of the time when radioactive decays happen, they happen in a series of events to eventually get to something that is stable. Since this is not one of the normal ones, it's probably not stable. And so that undergoes a beta decay. And so if I write thorium 231 and 90, and it undergoes a beta decay, the one thing that I know is a beta decay is an electron, right? And that changes 0 mass, that has a -1. Okay? So what would be the element, or what would be the number of protons for the resulting product? 91. That element would be Pa, and its mass would be 231. Is that a normal version of the Pa? Ah, that is. Could be stable, or that could be radioactive. You don't know, but scientists do know. Okay? We actually have looked at every radioactive material, and we've done the decay series, and we know what they are. And so, if by chance we take a look at this, there are a number of radioactive decays that are required to actually get to a version that is stable. You never have to decide that. You just have to look up in the table to look at this. Now, one thing that we didn't identify, when an element or an atom becomes charged, it gets a new name. The generalized name is called an ion. Okay, an ion is something that has an imbalance of electrons and protons. It's either positive charge or negatively charged. Okay, elements before they react are always neutral. After they react, they are almost always ions. Okay. In particular, we can even give them subnames. Anything that has a positive charge is called a cation, and anything that has a negative charge is called an anion. If it's negative, it's an anion. If it's positive, it's a cation. We'll learn a little bit more about this. Cations are always written first. Anions are always written second. Okay, and this is one way in which we can create bonds between molecules because the positives and the negatives stick and attract just like magnets, and that can be a compound. It's one kind of compound that we're going to see being possible. But we wanted to, since we introduced the idea of positive and negative, we wanted to introduce the term. Ion is both, cation specifically positive, anion specifically negative. All right, when I look at the periodic table, again, I told you whole numbers are the atomic numbers, number of protons. You have whole numbers of protons. You never have a partial proton. Okay? But the number on the bottom is always an average. And so there are several different versions of carbon, but which is the most representative type of carbon? Big time, it's this one, mostly. Okay? What this number here means is the average mass. It is kind of like if I describe this class after the first exam, if I want to know how you're doing compared to, let's say, the other classes, how would I compare your performance versus everybody else, the other classes? What would I compare? The average of all of the exams. And so your guys' average is going to be well above the other two. Okay? I've got this feeling down in my heart. Okay? And so we got stuff writing on this. Now, come on now. You guys are going to be best. Now, how would I actually get the average for this class? Add them all up and divide by the number you have. Okay, here's the problem. When I'm talking about the number of things in terms of stuff that I can see, all right, we're not even towards billions. We're billions of atoms. So if I take and weigh them individually and divide by that very large number, it's not mathematically efficient, okay, to do that. So we have to calculate average mass a little bit differently, okay? And so what we're going to do is we're going to use percentages of the different versions that we have to actually calculate the mass. All right? Now, of this, probably over 97% of carbon is the 12 version, weighs 12. But the others attribute a little bit to the overall mass. And so there are percentages of each. If I take a look at any element, they all have isotopes. In this case, hydrogen has 3. Hydrogen, it's also called protium, deuterium, and tritium are the 3 isotopes. You can see it weighs 1, it weighs 2, or it weighs 3. The difference is it has a different number of neutrons. The element doesn't change because the element is defined by having 1 proton. There are some influences by having neutrons. The tritium is radioactive. It's too large, it's unstable, it's radioactive. The deuterium, just having that nucleus, all the reactions are the same. They just do it at a different rate. They don't react as fast as protons do. Okay, a little bit heavier, a little bit slower, so it takes a little bit longer for them to do the things. But everything has isotopes. And the isotope is an element that has different number of neutrons. Or you can say it a different way, different number or different weights. Okay? And so we always use the average. Okay? and they're weighted by their relative abundance and percentage. And so, in this, if we actually look at the two largest versions of carbon, carbon 12 and 13, they have exact masses, and look at how many decimal places they go out to, right? And they have exact percentages, and at least at that percentage, the carbon 14 and carbon 11 don't even represent yet. Okay? And so if we take this and wanted to solve what the average mass is, okay, what we would have to do is change each percentage into a decimal point so we can do mathematics. We multiply each of the exact masses times that decimal to get a value. And then we add those values together. Okay? That's one way. I can straight up give you the percentages and the masses. You would multiply out 0.982, okay, to do this, 0.98882 times 12.00000 forever. AMUs, and you get a number. AMUs. Then you would change this one to 0.01108 times this exact mass, AMU, and you'll get a number. What you do is you add them together, multiply and add, and you will get the answer. In this case, how many significant figures can you give the answer to? Because CHEM-111 is very picky, right? What is the 4? You can give it to 4 because there are 4 here in the multiplication. And when you add, you're going to have a lot of decimal places, so that will be your limiting factor on that one. When you do it all out, CHEM-111 will be picky to whatever the 4th digit is. All right. There's another way to calculate. Sometimes, that's way too easy. That's way too easy. That's not the kind of problems you're going to have. All right. If I give you both of the percentages, what I'm going to do is I'm going to give you something else. All right. Now here's an example. Just what I told you. Okay. All of the percentages. Okay. Come on. Times, multiply, add everything together, and then in this case it can only be 3 sig figs. Okay. Too simple. This is what I'm going to give you more often, is this. Calculate which element, one of the elements, okay, if I have an average weight of that. Okay. And what I'm going to tell you is, okay, in this case, you're going to have 2 x's. All right? You get the average weight right there. And then you're going to have 2 things. One that has a certain percentage, x, okay, and the other is 1 minus x, because you have 100%. Okay? You'll have one of them as a known value, and the other one would be enough to add up to 100%. So mathematically, I take 1 representing 100 minus whatever the other one is, and the other one comes out with x. Here's the key. CHEM-111 is going to ask you for the percentage of one of them. You have to find both, but it's going to ask you for the percentage of one of them. Always put x with the one you're supposed to look for. Saves you a step. Okay? Here's where algebra comes in. One of them is multiplied by 1 minus x. One is multiplied by x. Distribute the numerical value. Distribute the x. I now have an x value and an x value. Okay? Combine those 2 x values into one single x value. A numerical number, get those together. and then you find x by dividing both sides. Okay? That's way too simple. I've got 3 unknowns. What do I do? Okay? You make one of them x because you don't know it. Okay? One of them has a known value. Convert that to decimal. So there's your x. So what is left? Okay? What's left is 1 minus, you already know some of it, so that's what's left, minus the x. Mathematically, then you can solve for x itself. What if you have 4 things? What do they have to give you? They have to give you 2 knowns to distribute the 2 things that are unknown. You may find some that have 4. You may have some that have 3. There may be very nice and only have 2, but you probably won't give both percentages and actually calculate the value. That's probably not what CHEM-111 is going to do for you.